Some of us were taught in high school that the electron orbits around the nucleus, like a planet around the sun. However, this description has been understood as a gross misrepresentation for the better part of the last century. As it turns out, there is a characteristic uncertainty related to the very small. No one can tell exactly where something is. The best one can do is figure out where something is most likely to be. We can visualize this with something called the probability cloud. Here, we see the probability cloud of a proton at the center of a hydrogen atom. The denser regions are where the proton is more likely to be found. However, this uncertainty is not due to an inability of ours to measure the small in an exact manner. It is a fundamental aspect of the world in which we live, and its implications are extraordinary. Let us take, for example, the phenomenon of tunneling. If we can't tell exactly where something is, then it follows that we can't tell exactly where it's been or where it will be. The best we can hope for is where it most probably will be. So there's a small chance that a rocket ball thrown repeatedly at a barrier could just tunnel through the barrier, appearing almost magically on the other side. We don't see this often because a rocket ball is pretty big and its uncertainty pretty small. But if we deal with matter on the subatomic scale, it becomes much more likely. Here our projectile approaches the barrier. We see here its probability cloud. Although it's most likely near the center of the cloud, we can see that there is a small chance of it being on the other side of the barrier. And so, sometimes, it is. Tunneling isn't a mathematical trick or an assumption. It's an observable fact. It's made use of commonly in modern electronics, and in a real way, allows for life on Earth. To see why, let us trace the creation of a photon in the sun. The light from the sun that we see reflected off the moon, the light which drives the Earth's weather, that provides the energy for life, all originates from the process of nuclear fusion in the sun. Two light atomic nuclei collide, forming a new element, and in the process, light is released. But these nuclei are both positively charged and so repel each other. Only if they have enough energy can they overcome this potential barrier and fuse. But if you do the math, the nuclei in the sun don't have enough energy. The sun's just not hot enough. Nonetheless, the sun shines, and it does so because of tunneling. Just like our physical barrier, there's a chance that our particles will be on the other side, and so the sun shines.
All right. Look here. Oh. All right, so just like all along, you don't have to copy exactly what I have, but you can copy anything I have. So here's some stuff I got out of that. Right? Now you guys know that particles at the quantum level exist probabilistically. So where is something? It's kind of all spread out according to Schrödinger equation. Right? So you think of this like this probability cloud, right? Where if there's a high chance that it's kind of in the center of this cloud, but there's a small chance somewhere on the periphery. Right? What if you have like some barrier here? You've got a barrier. Right? Well, for the Schrödinger equation, every once in a while the particle might actually pop up on the other side of this barrier. Right? Of course, we're talking about like atomic size, right? And so a little bit of self-explain. He mentioned a couple examples, right? So like nuclear fusion in the sun, right? So if you say like how hot is the sun, how much pressure is there near the core of the sun, how much what temperature and pressure would it take to initiate a fusion reaction? It doesn't quite add up unless you also consider this quantum tunneling effect. Right? So sometimes each hydrogen atom will be a little out of place from where it should be, and that's enough to initiate fusion into helium that might not otherwise. Right? Another example is modern electronics. So electronics are always getting smaller and smaller. Right? Anything digital, like that video you just watched, well, that was all digital. If you're watching this video that I'm recording right now, it's all digital, right? So it's just a string of zeros and ones. Well, how do you represent zeros and ones? Right? Well, maybe the smallest you could do is like some kind of atom or some version of that, right? Something on its scale. But once you get so small, then you're going to run up into barriers like this, like the Heisenberg uncertainty principle, like quantum tunneling, or maybe a particle will be like out of place from what it should be, right? Cosmic ray hits it, right? So that's caused issues before, where sometimes we want to flip to zero or vice versa from just things being like atomic size like that. All right. Ooh, this next one. Are you guys ready for entanglement? All right, so quantum entanglement. This one is it's a lengthier video. It's about 9 minutes long. You have to think pretty deeply on this. Ideally, you might watch this, go back and watch it a few times, but I'll play it once. But think deeply and yeah. Here's a weird one.
In the 1930s, Albert Einstein was upset with quantum mechanics. He proposed a thought experiment where, according to the theory, an event at one point in the universe could instantaneously affect another event arbitrarily far away. He called this spooky action at a distance because he thought it was absurd. It seemed to imply faster than light communication, something his theory of relativity ruled out. But nowadays we can do this experiment, and what we find is indeed spooky. But in order to understand it, we must first understand spin. All fundamental particles have a property called spin. No, they're not actually spinning, but the analogy is appropriate. They have angular momentum and they have an orientation in space. Now we can measure the spin of a particle, but we have to choose the direction in which to measure it. And this measurement can have only one of two outcomes. Either the particle's spin is aligned with the direction of measurement, which we'll call spin up, or it is opposite the measurement, which we'll call spin down. Now, what happens if the particle's spin is vertical, but we measure its spin horizontally? Well, then it has a 50% chance of being spin up and a 50% chance of being spin down. And after the measurement, the particle maintains this spin. So measuring its spin actually changes the spin of the particle. What if we measure spin at an angle 60 degrees from the vertical? Well, now, since the spin of the particle is more aligned to this measurement, it will be spin up 3/4 of the time and spin down 1/4 of the time. The probability depends on the square of the cosine of half the angle. Now, an experiment like the one Einstein proposed can be performed using two of these particles, but they must be prepared in a particular way. For example, formed spontaneously out of energy. Now, since the total angular momentum of the universe must stay constant, you know that if one particle is measured to have spin up, the other, measured in the same direction, must have spin down. I should point out it's only if the two particles are measured in the same direction that their spins must be opposite. Now, here's where things start to get a little weird. You might imagine that each particle is created with a definite, well-defined spin, but that won't work, and here's why. Imagine their spins were vertical and opposite. Now, if they're both measured in the horizontal direction, each one has a 50-50 chance of being spin up. So there's actually a 50% chance that both measurements will yield the same spin outcome. And this would violate the law of conservation of angular momentum. According to quantum mechanics, these particles don't have a well-defined spin at all. They are entangled, which means their spin is simply opposite that of the other particle. So when one particle is measured and its spin determined, you immediately know what the same measurement of the other particle will be. This has been rigorously and repeatedly tested experimentally. It doesn't matter at which angle the detectors are set or how far apart they are, they always measure opposite spins. Now just stop for a minute and think about how crazy this is. Both particles have undefined spins, and then you measure one, and immediately you know the spin of the other particle, which could be light years away. It's as though the choice of the first measurement has influenced the result of the second faster than the speed of light, which is indeed how some theorists interpret the result. But not Einstein. Einstein was really bothered by this. He preferred an alternate explanation, that all along the particles contained hidden information about which spin they would have if measured in any direction. It's just that we didn't know this information until we measured them. Now, since that information was within the particles from the moment they formed at the same point in space, no signal would ever have to travel between the two particles faster than light. Now, for a time, scientists accepted this view, that there were just some things about the particles we couldn't know before we measured them. But then along came John Bell with a way to test this idea. This experiment can determine whether the particles contain hidden information all along or not. And this is how it works. There are two spin detectors, each capable of measuring spin in one of three directions. These measurement directions will be selected randomly and independent of each other. Now, pairs of entangled particles will be sent to the two detectors, and we record whether the measured spins are the same, both up or both down, or different. We'll repeat this procedure over and over, randomly varying those measurement directions. to find the percentage of the time the two detectors give different results. And this is the key, because that percentage depends on whether the particles contain hidden information all along or if they don't. Now, to see why this is the case, let's calculate the expected frequency of different readings if the particles do contain hidden information. Now, you can think of this hidden information like a secret plan the particles agree to, and the only criterion that plan must satisfy is that if the particles are ever measured in the same direction, they must give opposite spins. So, for example, one plan could be that one particle will give spin up for every measurement direction, and its pair would give spin down for every measurement direction. Or another plan, plan 2, could be that one particle could give spin up for the first direction, spin down for the second direction, and spin up for the third direction, whereas its partner would give spin down for the first direction, spin up for the second direction, and spin down for the third direction. All other plans are mathematically equivalent, so we can work out the expected frequency of different results using these two plans. Here, I'm visually representing the particles by their plans, their hidden information. With plan 1, the results will obviously be different 100% of the time. It doesn't matter which measurement directions are selected, but it does for particles using the second plan. For example, if both detectors measure in the first direction, particle A gives spin up while particle B gives spin down. The results are different. But if instead detector B measured in the second direction, the result would be spin up, so the spins are the same. We can continue doing this for all the possible measurement combinations, and what we find is the results are different 5 out of 9 times. So using the second plan, the results should be different 5/9 of the time. And using the first plan, the results should be different 100% of the time. So overall, if the particles contain hidden information, you should see different results more than 5/9 of the time. So what do we actually see in experiment? Well, the results are different only 50% of the time. It doesn't work. So the experiment rules out the idea that all along these particles contain hidden information about which spin they will give in the different directions. So how does quantum mechanics account for this result? Well, let's imagine detector A measures spin in the first direction and the result is spin up. Now, immediately you know that the other particle is spin down if measured in the first direction, which should happen randomly 1/3 of the time. However, if particle B is measured in one of the other two directions, it makes an angle of 60 degrees with these measurement directions. And recall from the beginning of this video, the resulting measurement should be spin up 3/4 of the time. Since these measurement directions will be randomly selected 2/3 of the time, particle B will give spin up 2/3 times 3/4 equals half of the time. So both detectors should give the same results half of the time and different results half of the time, which is exactly what we see in the experiment. So quantum mechanics works, but there is debate over how to interpret these results. Some physicists see them as evidence that there is no hidden information in quantum particles, and it only makes sense to talk about spins once they've been measured. Whereas other physicists believe that entangled particles can signal each other faster than light to update their hidden information when one is measured. So does this mean that we can use entangled particles to communicate faster than light? Well, everyone agrees that we can't. And that is because the results that you find at either detector are random. It doesn't matter which measurement direction you select or what's happening at the other detector, there's a 50-50 probability of obtaining spin up or spin down. Only if these observers later met up and compared notebooks would they realize that when they selected the same direction, they always got opposite spins. Both sets of data would be random, just the opposite random from the other observer. That is indeed spooky, but it doesn't allow for the communication, the sending of information from one point to another faster than light. So it doesn't violate the theory of relativity. And that, at the very least, would make Einstein happy.
All right. Over here. So here's one I got a poster for, hanging from my ceiling. Right, about that. Right, so sort of a copy of that here. Yeah, so spooky action at a distance was Einstein's phrase for this. Right? Because, right, so to recap what he was saying, while you guys are trying some stuff about this. If you have a pair of entangled particles, right, so two particles, right, the angular momentum between them would be 0, and then you separate them out, right, and then you detect their spins. Now, remember, in quantum mechanics, spin, like anything else, is probabilistic, not exactly determined. Or it's not like you throw a curveball and say, oh, it was clearly spinning about that axis, right? Like a baseball, right? We're talking about particles, right? So it's going to be probabilistic as to how it spins, right? So I have a couple of detectors, and they're separated by some huge distance. I didn't mean to make them overlap like that. So more like this. So huge distance between the two, right? Right. And then one detector detects one of the particles spin up. Well, because of conservation of angular momentum, the other one must be spin down. Okay, so that seems like it makes sense. Like all fine and good, right? Problem is that this happens instantaneously. So even if the distance between these two detectors is really large, the information would travel faster than the speed of light. Right? Well, Einstein was interpreting this as, well, okay, well, maybe there is some kind of what he was calling hidden information. The information is already embedded in the particles that would cause it to be like spin up or spin down, right? Because that would be able to explain this away without having faster than light travel of information. Right? But along comes that John Bell experiment in 1964 that ruled out that hidden information. And a lot of that video was running through this experiment. Okay. So the information actually does travel faster than light. So back a week or two ago when I told you guys that there's this cosmic speed limit, the speed of light, nothing can travel faster than the speed of light. And we ran into sort of a couple of exceptions. One was universal expansion, just because of how the universe expands, like everywhere. You could have two distant galaxies moving away from each other faster than the speed of light, although they're not moving through space faster than the speed of light, so maybe it doesn't violate from that point of view. And this is sort of the other exception to that, right, is that quantum entanglement, entangled particles, the spin information can, in fact, verified by this 1964 experiment by John Bell, travel faster than the speed of light. But maybe the caveat is that it is random information. So could you use this to turn this into a technology where you could like send email faster than the speed of light? Well, that appears to be not the case. All right. You guys good there? You guys good with quantum entanglement? All right. Check out next one. Fate or free will?
Newtonian determinism says that the universe is a clock, a gigantic clock that's wound up at the beginning of time, and it's been ticking ever since according to Newton's laws of motion. So what you're going to eat 10 years from now on January 1st has already been fixed. It's already known using Newton's laws of motion. Einstein believed in that. Einstein was a determinist. Well, does that mean that a murderer, a horrible mass murderer, isn't really guilty of his works because he was already preordained billions of years ago? Einstein said, well, yeah, in some sense that's true. Even mass murderers were predetermined, but he said they should still be placed in jail. Heisenberg then comes along and proposes the Heisenberg uncertainty principle and says, nonsense. There's uncertainty. You don't know where the electron is. It could be here, here, or many places simultaneously. This, of course, Einstein hated because he said God doesn't play dice with the universe. Well, hey, get used to it. Einstein was wrong. God does play dice. Every time we look at an electron, it moves. There's uncertainty with regards to the position of the electron. So what does that mean for free will? It means in some sense, we do have some kind of free will. No one can determine your future events given your past history. There's always the wild card. There's always the possibility of uncertainty in whatever we do. So when I look at myself in a mirror, I say to myself, what I'm looking at is not really me. It looks like me, but it's not really me at all. It's not me today, now. It's me a billionth of a second ago, because it takes a billionth of a second for light to go from me to the mirror and back.
Oh, no. All right, so there's this question that's probably popped up in some of your other classes, maybe your English classes or psychology classes, of you know, how much free will do you have, right? Or how much is fated? Or maybe the sort of psychology take on that is like how much is nature versus nurture? Not exactly the same question, but maybe adjacent to that, right? And okay, so here's sort of the physics take on this, right? If you take Newtonian determinism to its logical end, then everything would sort of have to be fixed, right? So go back to fall semester when we were talking about like momentum, for example, like conservation momentum, energy, and right? Is that if you had universal information about the momentum of particles, right? Their mass, velocity, direction, the whole thing, right? Then everything that's about to happen, well, you can determine, right? Kind of like if you have a billiards table, right? You strike the cue ball, right? And that's gonna everything. Once you strike the cue ball, everything that's gonna happen in the next few seconds is like determined, right? It's just a matter of time before it plays out, right? Well, how about like your own decisions? Well, where do those come from? Like, what is your mind sort of, right? Well, your mind has to interact with the physical world, like through your brain, which is made out of matter, just like protons, neutrons, and electrons, and right, everything on the periodic table. So, does that put it into the realm of physics? And it again, if you go back to quantum, Newtonian determinism, Newtonian mechanics, right? Then maybe everything's sort of played out. It's just like waiting to happen, right? So how could you even possibly have the chance of like deviating from that? Well, quantum mechanics at least allows for a possibility of uncertainty, right? Heisenberg uncertainty principle, Schrodinger equation, right? Probabilistic nature of things. Right? So this might possibly have an angle on giving you like, some kind of free will over like fate determinism. Right? It's an idea. Yeah. All right, you guys ready for the standard model?
The objective of particle physics is to understand the basic structure and laws in nature, all the way from the largest dimension in the universe, formation of galaxies and stars, all the way down to the smallest dimension in the microcosm.
So historically, we knew about all of the different elements in nature. We knew about helium, hydrogen, oxygen, gold, lead, and so on, which are all made of different atoms. But a great simplification was made when we realized that all the atoms are just made out of three particles, the protons, the neutrons, and the electrons. And just by adding more protons, more electrons, we get a different element, different type of atom.
In principle, you can build a very simple universe with just protons, neutrons, and electrons.
But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays.
There wasn't really a system established to organize this zoo of particles.
So we were calling these new particles things like pi, sigma, delta, and so on. And things got so bad, we were running out of symbols to name these particles. So we started organizing these particles according to the properties they have. And the properties are things like spin, electrical charge, so if they're positively charged, negatively charged, or neutral, mass of the particles, and the lifetime of the particles, which is how long it takes before they decay into lighter particles.
To simplify the picture, new fundamental particles called quarks were predicted. And the whole zoo of particles could be described by combinations of these quarks. And this was the birth of the Standard Model. At the beginning, there were only 3 quarks. Then a 4th, 5th, and 6th quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They are composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the Standard Model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks, The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together.
The Standard Model is extremely successful, and it has predicted all the phenomena we have seen so far at the microscopic level.
This is a beautiful theory. It is self-consistent, it's predictive, but it's incomplete. There's one last missing piece of this puzzle. That's the Higgs boson. It's the holy grail of particle physics.
We know exactly what it should look like, and we have predicted this particle since over 40 years, and we use it in all our calculations and so on. We're pretty sure it's there, but we haven't found it so far. And now the LHC, which is already running, taking data, will find this particle if it exists. So this is the final piece of the Standard Model that we're looking for right now.
But there are still many unanswered questions beyond the Standard Model.
Some of the things that Atlas could discover that are beyond the Standard Model are things like dark matter, supersymmetry, or even extra dimensions.
All these open questions point to the existence of new particles, which could be discovered and studied here at the Large Hadron Collider.
All right, look over here. Right, so one of my posters is a Standard Model. It looks like that. And if you're thinking that looks kind of like the periodic table, well, it's sort of analogous to it. Right? So when you guys took the class chemistry, you had the periodic table of the elements, about 100 or so elements. Right? And those could be the basic building blocks of all ordinary matter, say like in this room. Right? But if you start thinking about it, well, every one of those elements is really made out of protons, neutrons, and electrons. So maybe more fundamentally, that's the building blocks of matter. Okay? And if you go to a particle physicist, they say, oh yeah, that's actually a step in the right direction. And they would pull up the Standard Model. Okay? So we've got these 17 elementary particles. Right now there are 12 of these, they call it fermions. Right? And then these 5 bosons. Right? Right? So like the photon is the example of a boson, right? The electron is the example of one of these fermions, one of these leptons, right? These are organized by a mass, charge, and spin, right? Kind of like periodic table, right? Has certain organization by like mass. Right? So mass, charge, and spin. Okay. So even though the electron is one of these elementary particles, right? So you can't really like, break this in half, right? But interestingly, protons and neutrons are not. Protons and neutrons are made out of up and down quarks, right? So 2 up and a down for a proton, 1 up and 2 down for a neutron, right? And then there are these other particles too that show up in the Standard Model. Right? Now, these are all verified experimentally based on these collisions at these particle colliders. Right? Now, why are there like 17 particles and like not more or less? Sometimes there's been called a kind of an ugly model in some sense. Also, does this explain things like, well, there's some mysteries that maybe this doesn't quite connect to, like, so how could you explain like dark matter, dark energy, right? Doesn't seem to be good explanation here. All right, so you guys got that Standard Model? All right, so now let's look at one of these, the Higgs boson. Oh, I meant to mention too, that video you guys just rolled was a bit outdated because it was like a year after that video was released that the Higgs boson was experimentally verified to exist. So that's the next one we're doing, Higgs field, Higgs boson, and mass. All right, I got a 3-parter here for you guys.
Let's cut to the chase. As of July 4th, 2012, the Higgs boson is the last fundamental piece of the Standard Model of particle physics to be discovered experimentally. But you might ask, why was the Higgs boson included in the Standard Model alongside well-known particles like electrons and photons and quarks if it hadn't been discovered back then in the 1970s? Good question. There are 2 main reasons. First, just like the electron is an excitation in the electron field, the Higgs boson is simply a particle which is an excitation of the everywhere permeating Higgs field. The Higgs field, in turn, plays an integral role in our model for the weak nuclear force. In particular, the Higgs field helps explain why it's so weak. We'll talk more about this in a later video, but even though weak nuclear theory was confirmed in the 1980s, in the equations, the Higgs field is so inextricably jumbled with the weak force that until now we've been unable to confirm its actual and independent existence. The second reason to include the Higgs in the Standard Model is some jargony business about the Higgs field giving other particles mass. But why does stuff need to be given mass in the first place? Isn't mass just an intrinsic property of matter, like electric charge? Well, in particle physics, no. Remember that in the Standard Model, we first write down a mathematical ingredients list of all the particles that we think are in nature, and their properties. You can watch my Theory of Everything video for a quick refresher. We then run this list through a big fancy mathematical machine, which spits out equations that tell us how these particles behave. Except, if we try to include mass as a property for the particles on our ingredients list, the math machine breaks. Maybe mass was a poor choice, but most particles we observe in nature do have mass, so we have to figure out some clever way of using ingredients that will spit out mass in the final equations without it being an input. Kind of like how you can let yeast, sugar, and water ferment into alcohol that wasn't there to begin with. And as you may be thirstily anticipating, the solution is to toss a yeasty Higgs field in with the other ingredients of the Standard Model, so that when we let the math ferment, we get out particles that have mass. But this model also brews up something we didn't intend, a solitary Higgs particle, the infamous boson. And since the model works so well to explain everything else, we figured it was pretty likely that the lonely boson is right too. To summarize, the Higgs boson is a particle which is a leftover excitation of the Higgs field, which in turn was needed in the Standard Model to 1. Explain the weak nuclear force, and 2. Explain why any of the other particles have mass at all. However, the boson is the only bit of the Higgs field which is independently verifiable, precisely because the other bits are tangled up in the weak nuclear force and in giving particles mass. The fact that the Higgs boson is so independent from the rest of the Standard Model is why it's the last piece of the puzzle to be discovered. And if it turns out to be exactly what was predicted, the Standard Model will be complete. The only problem is that we know the Standard Model isn't a complete description of the universe. It entirely misses out on gravity, for example. So to physicists, it would be much more interesting and helpful if the Higgs boson turns out to be not quite what we expect. Then we might get a clue as to how to reach a deeper understanding of the universe. So even though we just made a discovery, we can't sit back and relax. We need a hint, Mr. Higgs. Let's cut to the chase. How does the Higgs field give particles mass? And to be clear, we're talking about the Higgs field and not the Higgs boson, which is merely an excitation left over after the process we're about to explain. But I digress. Back to mass. To begin, we need to know what we even mean by mass. So we'll head the other direction and talk about what it means to be massless. This may sound crazy, but the defining feature of any particle without mass is that it travels at the speed of light. In fact, if we're honest, it should really be called the speed of massless particles. But since the first massless particles we knew about were photons of light, the name has stuck. Anyway, the point is that all massless particles travel 300 million meters every second. The details of this are explained by special relativity, but simply put, it's physically impossible for a massless particle to not travel at 300 million meters per second. And so mass is just the property of not having to always travel at the speed of light. As a side effect, this also means not being able to travel at the speed of light. But the key is that
Hang on. Let me pause this. Pause. All right, recording resumed.
particles with mass are lucky enough that they get to travel at any speed they want, as long as it's slower than light. The amount of mass something has just tells how hard it is for it to change from one of these speeds to another. Now, in part 1, we mentioned that if there were no Higgs field in the Standard Model, all particles should be massless and thus travel at the speed of light. But you and I and Swiss cheese clearly have mass, because we have the beautiful luxury of being able to sit still. So how does the Higgs field help us do that? Well, while massless particles can only travel at the speed of light, they are allowed to bounce off of things. Things like particles, which are really just excitations in a quantum field. For example, the electron field is more concentrated at certain places, called electrons, and everywhere else is empty space. But the Higgs field is unusual in that it has a high value everywhere. And to be clear, this high value is not the famous Higgs boson. That's an extra excitation in addition to this already elevated field. But because the Higgs field has this everywhere non-zero value, any particle that can interact with it is pretty much bouncing off of it all the time. And if a massless particle bounces back and forth, or since it's quantum mechanics, does both at the same time, then even though in between bounces it travels at the speed of light, when you add everything up, it looks like the particle is going slower than light, maybe even like it's not moving. And since only things with mass are allowed to not move, our massless particle now looks and acts like it has mass. Well done, Higgs. What's more, the Higgs field can even interact with its own excitations, which is to say, it can give mass to the Higgs boson too. Actually, the Higgs field likes to interact with itself so much more than with the lowly electrons and protons that make us up, that the Higgs boson has a great deal more mass. But we shouldn't complain, because even though the Higgs has given us a lot of trouble and only a little bit of mass, at least we have mass, which allows us the simple pleasure of not moving. Suppose you want to discover a particle. First, you need.
Wait a second, Henry. Did you just say that you're setting out in advance to discover a particle? How is that even discovering? Isn't that a little like Europeans discovering continents where millions of people already live? I mean, it's not really discovery, is it? It's more scientific fact checking.
Exactly. Thanks for walking us through that point, John. If we're honest, we should say that the mathematical model for the Higgs was discovered in the 1960s, but the particle itself wasn't confirmed until 2012. In fact, the Higgs boson isn't even the first new particle to be uncovered at the Large Hadron Collider. The Xi-b particle, basically a heavy version of the neutron, was actually found several months earlier. You probably didn't hear much about it because the Xi-b is just a combination of quarks that we already know exist, so it's not really that exciting. I mean, if you know about cheese and you know about crackers, then the discovery of cheese and crackers, as delightful as it may be, isn't likely to upend your universe. But the standard model of particle physics also predicts something beyond cheese and crackers. That is, about 1 out of every bajillion collisions should produce a Higgs boson, which then decays into everyday stuff like electrons and photons, which are the same crumbs we catch in the detector all the time. This battle between the tiny chance for a collision to have produced a Higgs-like particle versus all the trizillion other collisions that produce similar crumbs is part of why we need a big machine like the Large Hadron Collider at all. There were earlier accelerators that had enough energy to create Higgs bosons in principle, but they couldn't actually do enough collisions to be confident they were actually seeing a Higgs boson and not just an assortment of crumbs that looks by chance like it's from a Higgs boson. It's kind of like trying to find out if a 20-sided die is rigged. Maybe you suspect it's twice as likely to land on a 3 than on any of the other numbers, but how can you check? Well, that sounds easy enough. Just roll the die a few times, and if you see extra 3s, it's rigged, right? Not so fast. For example, if you roll the die 10 times, there's a pretty good chance that you won't get any 3s at all. That's because even though rolling a 3 is twice as likely as each other number, there are still a lot of other numbers you could roll. So random chance and big numbers can be surprisingly deceptive. Even if you roll the die 100 times and do get an excess of 3s, this is still expected to happen with a fair die once every 50 times. How much are you willing to bet that you actually have evidence for a new particle if there's a 1 in 50 chance you'd get these results by random fluctuation even if the particle doesn't exist? What if a Nobel Prize is on the line? How sure do you want to be? 1 in 1,000? 1 in 10,000? Actually, physicists are even more stringent. When we say we've discovered a particle, it's because if the particle didn't exist, there would be less than 1 in a million chance of us getting the results that we do. So if you want to convince a particle physicist that you've discovered an unfair die, you'll need to roll it over 550 times to satisfy them. And that's just to check if a 20-sided die is rigged. There are far more than 20 possible outcomes of a high-energy particle collision. So in order to be confident about announcing evidence for a new particle at the LHC, you need around 600 million collisions every second for 2 years. Only then can you uncork the wine to go with your cheese and crackers and claim a successful successful scientific fact-checking.
All right. So it's gonna be the one we're gonna wrap up with today. Okay, so here's some stuff I got out of those. All right, that's in 3 parts. Okay. So what is this Higgs boson? Again, this was the last part of the standard model to be experimentally verified. That was in 2012, right? And the boson is really just an excitation in what's called the Higgs field. Maybe the Higgs field is the more important thing to focus on here. Okay? So some particles interact with this field and some don't. Right? Anything that does not interact with the Higgs field does not have mass. So for example, photons. Photons are massless, right? The more a particle interacts with the field, the more mass it'll have. So the more inertia it'll have. So from a particle physics point of view, that's what gives anything like mass or inertia, right? Is this interaction with this everywhere permeating Higgs field, right? And if this Higgs field exists, again, this was worked out in theoretical physics like many decades ago, right? Then sometimes you should expect to see this this excitation in the Higgs field, and that's what the Higgs boson is. That's this boson, right? Finally, that last bit that I played you referenced something from statistics, right? One of the reasons, not the only reason, but one of the reasons that I introduced this whole topic of quantum mechanics with statistics is this right here. So how does a particle physicist verify the existence of a particle that was worked out in the physics theory, right? Well, it's called a 5 sigma standard, right? So you guys remember that Z table only went from like -3.5 to 3.5, and that covers like 99 point something percent, like 99.98 I think percent of all possibilities, right? So to be out here on the tail, remember one of the examples I told you guys, one of the analogies was, suppose we're aliens up in a spacecraft, we're looking down, watching everybody walk around, right? And we hypothesize that there's such a thing as basketball going on in these arenas, right? We can't see it, but we think there is. And some evidence that would support this is if you see groups of 5 people walking around that are all like very tall, right? So all groups of 5 very tall people, right? That you wouldn't expect to see if it was all random, but you would expect to see occasionally if such a thing as basketball exists, right? So replace tall people or like height with things like mass, charge, and spin. Replace basketball with Higgs boson, and now you're looking at like 5 sigma standard verification of that particle, right? And now 5 sigma, we're talking about like it's like 3 in 10 million chance that it would be random, right? So you could be fairly certain that all this is holding up. All right, so that's going to be our pause point today, and we'll continue this adventure tomorrow.